Hello, Dr. Gao and everybody watching. Today I'm going to be demonstrating a tutorial on how to solve Bode plots as well as polar plots. So let's begin with the given example here. We have 3s plus 6 over s squared plus 7s plus 10. So my goal here is to manipulate this fraction so that it's easier to work with. So I'm going to begin by factoring out a 3 from the numerator so that we have 3 times s plus 2. And then in the denominator, I want something that adds up to 7 and multiplies to 10, and that's going to be 5 and 2, which is what we have here, s plus 2 and s plus 5. So then we can actually cross out s plus 2, and then we're left with 3 over s plus 5, which is what we have here. Now the key thing here to do is to manipulate what you have in the numerator and the denominator to this form right here, 1 plus j omega over x. Well, in our case, s equals j omega, so technically here you have 3 over j omega plus 5. So what can we do to manipulate this into that form? Well, from the numerator, we can't really do anything because we have a constant, we don't have an s, so we're going to pull out the constant. And I'm going to pull out 3 over 5, put it out front, and then we're left with 1 plus s over 5, which is perfect because that's what we wanted in the first place. Because, as we said, s does equal j omega over 5. In this case, 5 is our x. So then, now we're good to go. I want to start by doing the magnitude plot. So, as we said before, this term is going to actually help us solve what we have right here. So, because we're working with decibels, we're going to be using log. So, we're going to begin with 20 log of whatever we have first, which is our constant, 20 log of 3 over 5, minus 20 log of what we have here, which is 1 plus j omega over 5. The key thing to note here is that in the numerator, everything gets added, and the denominator, everything gets subtracted. So if we had another term out in front in the numerator, in the form that we wanted it to, it would be plus 20 log of whatever that number was. But in our case, we only have a constant, and we only have one thing in the denominator, so we just subtract them with each other. Then beginning with our magnitude plot, you have to know that your constant is going to be the number it equals, and then it's going to be a dotted line all across throughout the horizontal axis. So here, 20 log of 3 over 5 equals negative 4.44. So what I'm going to do is I'm going to take a different colored pen or marker, whatever you're using, and just dot it in dot it all the way across your horizontal axis. And then those dotted lines are not going to be your actual plot. They're going to be your guides to your actual plot. They're going to help you actually plot what you need. And then we're done with the first term. Then we have minus 20 log of 1 plus j omega over 5. Now, the good thing with this is that our x, in this case it's 5, gives us the starting point and whether to go up or down. So we're going to begin at 5, and then we're going to actually go down because of the minus 20 decibels per decade. So from here, I'm going to take my line. I'm going to dot from 5 minus 20 decibels per decade down. Okay? We don't have any more terms, so we're actually good to go. Now we can take our actual pen or marker that we're using, and we're going to begin until you hit a point. So begin with your constant until you hit a point. Now the only point we have here is 5. So I'm going to begin with negative 4.44. I'm going to keep going until I hit 5. So then I look at my dotted line at 5. 5 went down minus 20 decibels per decade. So I'm just going to follow it. We're going to go down minus 20 decibels per decade all the way, and it remains constant like that until it hits another term, but here we don't have any. So that is going to be your magnitude, sorry. Your phase, it's going to be similar, but not really. So as we said before, your constant is going to be the same throughout, but here your constant is actually going to start at 0, and it's going to be the same throughout. So here, you can't really see, but I did dot the horizontal axis. The next term we said was 5. So what I like to do is I like to go decibel below and a decibel above, decibel below and a decibel above the given x term. So here we had 5. I went down, a decade below or a decade above, not decibel. Decade below, which gives us 0.5, decade above, which gives us 50. So those are going to be what I'm working with. And then I also did the same here. I did 1, 10, 100. You don't have to do 1,000. I just did it for my sake. We dotted that. So basically, we were going up or down 20 or minus 20 decibels per decade. And the magnitude in the phase, you're going to be working with degrees, where you're going up. You're going to probably be going up by either 45 or 90. So here, we're going to be going from 0 until we hit our first point. Now, we said it was 5, but I did go a decade below. So now we're at 0.5. So I keep going until I hit 0.5. Okay, once I hit 0.5, my line goes down minus 45 degrees per decade. Now it's minus 45 because we said that the denominator does get subtracted. So we're going down minus 45 degrees per decade. So from 0.5 to 5, I should be at minus 45, which is where I'm at here, roughly. And then from 5 to 50, I should be at minus 90, which is why I'm here. So I just trace that line until I hit here. Your lines flatten out once you hit the decade above your x term. So if your x term was 3, your dotted line or your line flattens out once you hit 30. Just keep that in mind because we need that to keep going. Next, now that we have those two done, we can actually go into our polar plot. So here we're going to be looking at the magnitude, which is going to be our 3 over the square root of omega squared plus 5 squared. Keep in mind, this is the reason we're using that is because it's the magnitude. And then your polar is going to be the negative inverse tan of omega over 5. So what you do is you take this little chart right here. You're going to be with the omega, your number, and your angle. You're going to start with 0 and go to infinity. We're not going to actually plot all of them. We're just going to use those two terms. And then we're going to begin with our constant, which is 3/5 here. Once you plug in your constant into, so let's say you plug in infinity up into this equation, you're going to get 0 because you have such a big number in the denominator. You divide a small number by a big number, you're going to get 0. And then here, you plug it into this formula, infinity into this formula, and negative inverse tan of infinity over 5 is going to give you negative 90 degrees. So you're going to begin with your constant here, your polar. This is your polar graph. So this is how it's going to look. You're going to start with your constant, and we said we went to negative 90, so we're just going to go down until we hit negative 90, which is over here, right here. So let's assume one last thing. Let's assume we have another term in our denominator. Let's say we have 3 over 5, and let's say we have this term, and then we have another term, let's say 1 plus s over 3. Well, that doesn't really make this a lot more complex. All it does is just add another minus 20 log of 1 plus j omega over 3. Keep in mind you're subtracting because, as we said, denominators get subtracted. So we add this term here, and we just follow the same steps that we did. So you're going to keep going from your constant until you hit your point. In this case, your point is now 3 rather than 5. Keep in mind we're going to go down minus 20 decibels per decade because it's not squared. If it was squared, you'd go minus 40. But from 3 to 5, which is your next point, you're going to go minus 20. But once you hit 5, keep in mind 5 is also going down minus 20 decibels per decade. So you're going to actually subtract them together. So it's going to be minus 20 decibels per decade, and then you're going to add another minus 20 decibels per decade, and then you're going to be going down minus 40 decibels per decade from 5 until your next term. So that's kind of an overall look of what a function and its Bode and polar plots look like. So thank you so much for watching, and I hope you learned.